Can you? Okay. So in general physiology, what you have to understand is, first you have to understand the structure of cell. So before moving into the structure of cell, always remember the entire body is made up of cation and anion. That is a positive charge and a negative charge. So that is what your body entirely is built up of. So this positive ion, this what happens is, it when it is going to transport, it is not going to just go alone. It always going to be present with a sphere of hydration. That is what you call it as a sphere of hydration, what it is. So when you're going to have a sodium ion per se, when this sodium ion is present inside your body, it is not going to just stay as ionic state. It is going to be surrounded by a layer of water. So always when you're going to tell about the transportation of sodium, sodium will be always going along with water. Is it only applicable for sodium? No. All ions in your body attracts water. So whenever a ionic transfer is going to occur, it is going to be occurring along with your water. This is the first concept you are going to understand. So entire topic, general physiology, which I am covering, is going to be helpful for you for next exam, because this is based on the competency which is given by NMC. And we are going to talk about the what are the common questions asked in the university exam, and this is how your entire session is going to go. So now coming towards the sphere of hydration. So sphere of hydration, if I think you can understand what it is, then always you have two important state of any cell. Either it is going to be in a resting state or it is going to be a functional state. If it is going to be in a resting state, you always remember your ICF must be having negative charges and ECF must have positive charges. Only then there is going to be a resting membrane potential. You all know that the resting membrane potential is always negatively charged. Therefore, your internal, that is your ICF, is going to be negatively charged, whereas your ECF is going to be positively charged. When this negative charge of your ICF is going to slowly raise towards the positivity, only then it is going to change into functional aspect of the cell. That is what we call it as a depolarizing state. So what is a polarized state? That is the negatively charged ion, when it is present in the ICF, then you call it as a functional, so that is a resting state, that is going to be called as polarized state. Whereas when you call it a functional state, when both ICF and ECF is going to be positively charged, then you call it as a functional state, or you call it as a depolarized state. Okay, now coming towards the structure of a cell. Now this is your cell. So this is what you will be calling it as a cell. So what happens in this cell? Basically, in cell, you're going to have a membrane. So you're going to have a membrane. Okay, so what happens in the membrane? So when you're going to have a membrane, this membrane is going to be, either it is going to be a membrane towards your cells. Either membrane is going to be in your cells, or your membrane is going to be in your organelles, or it is going to be in your organelles. Is it clear? Am I audible? Someone, can you respond in the chat box whether I'm audible? Kirti, Uday, someone, can you respond in the chat box whether I'm audible? Thank you. So your membrane is going to be the covering for your cell, and either this membrane can be for a cell or it can be for a organelles. What does this membrane made up of? This membrane is made up of lipid. Always remember, if they are asking composition, it is going to be made up of lipid as well as protein. But when they ask what does your membrane made up of, your membrane is made up of lipid. What are the three kinds of lipids which are going to be present? Number one, it is going to be phospholipid. Number one, it is going to be phospholipid. Number two, sphingolipid. So number two is sphingolipid, and number three is going to be your cholesterol. Number three is going to be your cholesterol. These are the three important types of lipids which is present in your membrane. And what is the composition? So your composition is going to be, maina it is going to be made up of. So maina, your cells is going to be made up of, number one, protein. So what is the amount of protein which is going to be present? 55%. I'm just telling the important aspects of general physiology. No need to go in detail. When you read in a textbook, it is going to give lots of information. I'm just telling you what is important in that. So composition, number one, protein 55%, followed by it is your lipid. Lipid is going to be around 40%, and third is going to be your carbohydrate, which is going to be around 5%. Now coming towards this. So when you're going to see this important picture, what you can understand, your cell membrane is going to be like this. Okay, your cell membrane is going to be like this. So what is this round one and what is this one? So this is your phosphates. So the one which is going to be present in the bilayer like a sandwich. So always remember, your cells are going to be like a sandwich. So upper part is also a phospholipid, lower part is also a phospholipid. So upper part and lower part. So this is going to be a phospholipid which is going to be containing two important things. One is phosphate, one is lipid. Okay, where is going to be your lipophilic end and where is going to be a phosphate length? Always remember, I told you, your cell is going to be presented in the interstitial fluid. So there is between the two cells, you're going to have a fluid. Between the two cells, you're going to have a fluid. If between the two cells or fluids are going to be there, then always remember, lipid is it lipophilic or is it lipophilic or lipophobic? Okay, your lipid is hydrophilic or hydrophobic? Someone in the chat box, what is your lipid? A lipid is hydrophilic or hydrophobic? Someone can answer in the chat box. Is lipid hydrophilic or hydrophobic? This is what my question. Exactly. So your lipid is hydrophobic. If your lipid is hydrophobic, in that case, the lipid part, where it will be present, lipid part in the present, where it will be present, whether it is going to be present in the outer aspect or it is present in the inner aspect. Someone in the chat box. So you have a lipid, you have a phosphate, where your lipid will be present in the outer aspect or inner aspect, where it will be present. Exactly. Why it is inner aspect? Because very simple concept. It is going to be present in the inner aspect because outer aspect there is going to be a water. So since your water, it should not, it is a phobic. Therefore, your lipids will be in the inner aspect and phosphates will be in the outer aspect. So this is your phosphate and this is your lipid. As you can see, hydrophobic regions, okay, which is inside, and hydrophilic regions are outside. Okay, so there is a two leaflets. So two leaflets la you're going to have outer aspect and your inner aspect. Outer aspect la you're going to have a phosphate. Apart from phosphate, what are the other things that are present? Glycoproteins are present. Carbohydrate chains are present. I'll come to that later. Okay, now coming to the inner aspect. So in the inner aspect, you're going to have a lipid, isn't it? So what are the three important phospholipids which are present? So now what I am asking is, what are the three important phospholipids which are present in our cell membrane? There are three important things. Number one, all the things are called as phosphatidyl. Phosphatidyl. Okay, phosphatidyl is common. Either it is going to be phosphatidyl serine or it is going to be phosphatidyl ethanolamine. Ethanolamine, or it is going to be phosphatidyl inositol. Inositol. So these are the three important phospholipids which are present inside your cell. Okay, now you have a cell membrane. You know the major aspect of your cell membrane is going to be a lipid. So what are the different types of lipid? Phospholipid, sphingolipid, cholesterol. Adila phospholipid is the major one. What are the three important phospholipid? Phosphatidyl serine, phosphatidyl ethanolamine, phosphatidyl inositol. Then coming to your carbohydrate and your protein. So what are the carbohydrate? Always remember, your carbohydrate cannot be present as a free form. Always either it is going to be present along with protein or it is going to be present along with lipid. So with protein, you call it as a glycoprotein. With protein, you're going to call it as a glycoprotein. With lipid, you're going to call it as a glycolipid. Clear? Now coming towards your protein. Last and final, we are going to move towards the protein. So protein are two types. Either it is going to be, okay, either two times I'm going to tell. One thing is, either it is going to be attached to your lipid. Either it is going to be attached to your lipid. That is called as your peripheral protein. That is called as your peripheral protein. And either it is going to be, entire area. So your protein is going to be either attached with lipid or it is going to be present in the entire area. When it is present in the entire area, you call it as a transmembrane protein. You call it as transmembrane protein. Now you are clear with this, right? So this is what entirely we are talking about in the cell structure and function. So this is the first topic in your textbook. So this is going to be a competency PY1. In this PY1, this is what you need to know. Apart from this, others are not required. Okay, now coming towards the second important concept, that is your homeostasis. What is the homeostasis? Imagine what happens to your blood glucose level after you're going to take a food. It is going to raise, but it is not going to be raising so much. Okay, so what happens? Immediately, your body is going to sense. Who is going to sense that a beta cell is present in the pancreas? That is going to sense it, and your insulin is released. This insulin is going to bring back your blood glucose level to the normal. So it's going to bring back your blood glucose to the normal level. This constancy which is created inside your body, that is called as homeostasis. What is homeostasis? Near constant composition of your interstitial fluid. Always remember, your interstitial fluid is the one which is required to be corrected for maintaining the homeostasis. All our body parameters have to be maintained in the near normal level. This constancy is called as a homeostasis. Who coined this term? Very important. It is coined by Walter Cannon. How I can remember this? Remember it as VATCH. Watch. So Walter Cannon. Okay, Walter Cannon is coined the term homeostasis. So I remember like this. So you can also remember like this. Now, coming back to this homeostasis control process. So what happens? Your body is trying to attempt to maintain the interstitial fluid in a more or less constant environment. What is this constant microenvironment which I am talking about? This is called as milieu interior. This is what your Guyton textbook gives you. So what is the interstitial fluids microenvironment called as? Milieu interior. Who gave this term milieu interior? Milieu interior is coined by Claude Bernard. Claude Bernard. So he is the one who coined this term. How I am going to remember? CBI. So who is going to coin the term interior? Claude Bernard. So this is also one of the MCQ which they can ask you in your exam. So is it clear? Now coming towards your homeostasis process. Okay, your entire homeostasis process, it is going to be maintained by three important feedback mechanism. Number one is negative feedback mechanism. Always remember, there is two homeostatic process. Homeostatic process is three types. Number one is feedback mechanism. Number two is feed forward mechanism. Okay, well, first we will talk about this feedback mechanism. Feedback mechanism is of two types. One is either it can be positive feedback mechanism, or second one is going to be negative feedback mechanism. So what is positive feedback mechanism? So in positive feedback mechanism, nothing. Over there is a sense organ. So always remember, there is a sense organ. This sense organ is going to be sensing a particular variable. It is going to be sensing a particular variable. Okay, so once it is going to sense a particular variable, if there is any change, okay, what it does, it is going to activate some process. After activation of some process, there is going to be some process which is happening. Either there can be hormones generation, hormone stimulation, or some chemical messenger stimulation. Because of this, this is called as your positive feedback mechanism. Okay, so this process is going to be, again, it's going to be a cycle. Okay, positive feedback mechanism. So this is, sir, could you tell me the kinds of membrane lipids again? Very well, Uday, I'll tell you. So membrane lipids are of three types: phospholipids, sphingolipids, cholesterol. These phospholipids are again three types: phosphatidylserine, phosphatidylethanolamine, phosphatidyl inositol. Is it clear now, Uday? So shall I move towards the present topic? Yes. So this is going to be your sense organ. How it is going to go for a positive feedback mechanism. What is a negative feedback mechanism? When there is a excessive of this process that is going to occur. When there is excessive of process that is going to occur, that is going to stop your stimulation. That is called as a negative feedback mechanism. What are the examples of your positive feedback mechanism? Blood clotting, any parturition, that is your childbirth, or any action potential generation in a nerve, or last ditch stand. So what is this last ditch stand? You will definitely learn this in your cardiology part of your physiology. So CVS physiology, I will talk about this. Anyway, you just remember only this: coagulation of blood, childbirth, generation of nerve impulse. See here, what happens in a coagulation? So whenever there is going to be a degree of cell injury, blood vessel injury, that is going to activate the cascade of your coagulation. So greater the degree of clot formation, to the seal the ruptured blood vessel. So that is how it is going to occur. And similarly, your childbirth. So parturition. So when there is the nerve stimulation, okay, so when the head of the baby is going to push into your cervix, nerve impulses from your cervix are transmitted to your brain, that is going to be secreting oxytocin. This oxytocin is coming through your bloodstream to your uterus, and oxytocin is again stimulating contraction. This contraction in turn pushes your baby towards the cervix, and again the vice versa cycle occurs. So here there is no negative, it is a positive feedback mechanism. Similarly, third one is the generation of nerve impulses. So whenever there is going to be stimulation of nerve membrane, which is associated with a sodium influx due to the opening of sodium channel, the increase in the intracellular sodium is associated with further opening of your sodium channel. So already there is an opening of sodium channel. This is going to further increase your sodium channel. For example, there is a 6 rooms in your auditorium. So only one door is going to be opening. From that door, some person is coming inside. Then seeing that, what happens? All your doors are going to get opened and all are going to go out. So first, only one door opened, only few person went out. This further caused the stimulation for the others sitting in the auditorium to get outside the hall. Therefore, all the doors are opened and many people who are sitting inside the auditorium are going to get out. So that is what called as a positive feedback mechanism. Okay, now coming back to the negative feedback mechanism. Positive feedback mechanism, is there any doubt? Now shall I move towards the negative feedback mechanism? Yes, negative feedback mechanism in this type of control system, increased level of particular parameter. When there is an increase in the particular parameter, that is going to cause decrease of itself by a stimulation. So the response to the stimulus is going to be negative. For example, regulation of your atrial blood pressure, regulation of your CO2 levels within your circulation, hypothalamo-hypophyseal pituitary axis. All these things are going to be negative feedback regulation. So whenever there is an increase in the atrial blood pressure, that is going to be seen by the baroreceptors, and impulse are going to be relayed to the vasomotor center. There is going to be correction of vasomotor tone. Atrial blood pressure is going to decrease. Similarly, when there is a carbon dioxide level increase in the circulation, so it is going to be sensed by your respiratory center. It's going to step up the rate of respiration. Excess CO2 is expired. So therefore, it's going to be expired. Therefore, what happens? There is going to be resetting of your carbon dioxide level towards the normality. So all these things, example, your thyroid hormone or any hypothalamo-hypophyseal pituitary axis, all those hormones are going to be regulated by this negative feedback mechanism. Now, latest AIMS exam focuses on the gain. Okay, or you all know that your next exam most probably is going to be conducted by AIMS. Okay, so then you have to understand this gain mechanism. So that is why I'm going to take example. Let me tell you what is a gain in the negative feedback mechanism. So it is the measure of effectiveness. It's a measure of effectiveness of negative feedback pathway. So I don't know whether it's taught in your college by your faculties, but this important point is going to be very important for you, because you all are moving into the competency based things, and this gain is very important. So what is a gain? In a simpler term, gain is nothing but there is a correction by error. Always remember like this. What is a gain? It is a correction by error. I'll tell you an example. So what is normally what happens for a BP patient? Okay, so original value of BP. What is the original value of BP? Anyone? What is the original value of BP? Come on, tell in the chat box. What is the original value of BP? Sure, I'll send this all these notes in the WhatsApp group. No problem. Now just continue the class. You just tell me what is the normal. Exactly 120/80 is the normal. So let me take the systolic value alone. So systolic BP. So systolic BP value is going to be 120 millimeter of mercury. This is going to be the original systolic value. Now, because of some stress, because of some emotion, what happens? So when there is some stress or some emotion, you are going to be having 140 millimeter of mercury. This is your changed value. This is going to be your changed value. Now tell me what happens whenever there is going to be a stress, whenever there is going to be raise in the blood pressure, automatically what happens? Your body is going to sense it. Who is going to sense the rise in blood pressure? Vasoreceptors, baroreceptors. This baroreceptor is going to sense, and upon the activation of baroreceptor, your baroreceptor is going to correct it to 128 millimeter of mercury. Always remember, all the homeostatic process, all your corrections, it is not going to make it return to the normal value. It is going to try to make sure it comes to the normal value. That's why we call that homeostasis definition as near constant composition. It is not going to be completely reversing the action. It is going to be near total. It's going to be just taking you to the near normal. So near normal mechanism, it is going to bring you. That is what your homeostasis is. Therefore, your baroreceptor is going to take to the near normal, that is 128. Now tell me, what is the corrected value? So what is the corrected value here? Someone in the chat box, what is the corrected value? So this is your changed value. This is going to be your corrected value. So this is going to be called as corrected value. Okay, so what is going to be the correction occurring over here? So what is the correction that has occurred here? The changed value from your 140 millimeter of mercury, it has corrected towards 128 millimeter of mercury. So what is the correction done by your homeostatic mechanism here? Someone, what is the correction that is made by your homeostasis? Exactly, that is the answer is 12. Okay, so your correction is going to be 12 millimeter of mercury. Now, what is the error that had occurred? What is the error that has occurred? That is that difference between the corrected value and your normal value. So normal is 120 and corrected is 128. So now what is the error which is present? 8 millimeter of mercury. So now tell me, what is the gain? Gain is equal to correction divided by error. So your correction is going to be 12, error is going to be 8. So it is going to be nearly 1.2. Okay, now always remember your normal homeostatic mechanism, your gain of your baroreceptor should be less than 2. Your gain of baroreceptor should be less than 2. Now tell me, what is the gain? The degree of effectiveness with which a control system maintains a constant condition, that is determined by this gain. So any system that leaves the error is not 100% effective in preventing the damage. Imagine what would happen if the denominator becomes 0. Now let's imagine what happens when there is a denominator that is going to becoming 0. What is denominator? That is going to be error. Suttama, it is not going to leave any error. So it is going to be completely, it is going to correct. In that case, it is going to become gain is equal to, just imagine 12 by 0, which is going to be infinity. So your gain is going to be infinite. So in which one that is going to create a complete reversal to the normal mechanism, that is your renin angiotensin aldosterone mechanism, ROS mechanism. This is going to be helpful in correction of BP, but how this is going to be correcting in the long term? In long term, what it is going to do? It is going to bring back to the real normal condition, near normal condition. So here what happens? Your gain becomes infinity. This is called as infinite feedback gain principle. But this infinite feedback gain principle is not going to be 100% occurring. But what happens is, remember, whenever the system that is going to be short acting, here you will be having more error and you will be having less gain. Okay, in a condition where you're going to be, regulation is going to be a long acting, there you will be having more gain and less error. So this is what at the end of the discussion you should take home. So this is the take home message. Clear? So your gain indicates the effectiveness of the negative feedback mechanism. Now moving on towards the third important thing, positive feedback mechanism, we spoke already. Then we have spoken about the negative feedback mechanism. Now the third important thing is feed forward process. What is a feed forward process? Okay, here you are not going to get any stimulus like you got in your positive feedback and your negative feedback. Here there is no stimulus. Here there is no stimulus. Okay, or I can say, instead of telling a stimulus, I can tell it as there is no sensing variable. There is no variable that is going to act on your sense organs. Okay, sense organs directly, but instead it is going to be acting by anticipation, acting by anticipation. Can you remember what is a feedback for feed forward control? So here there is an anticipation of some changes, and it is going to be, sir, what is it? Complete reversal of. So very simple. Okay, Uday, it's very simple, pa. So what we are talking is a blood pressure. Normally, your baroreceptor is not going to completely reverse your blood pressure to the normal value. But renin angiotensin aldosterone mechanism completely reverses, at least near completely it is going to reverse. So 128 is what baroreceptor does. So from 120, it's going to be raising to 140. Once your baroreceptor is going to act, it is going to reduce to 128. That is near normal. Your this renin angiotensin aldosterone is a long-acting process where it is going to try to bring back your blood pressure to 120 millimeter of mercury itself. That is what I meant by complete reversal. Here, you will be having a more gain and less error. Whereas in a short-acting mechanism like your baroreceptor, you will have a more error and less gain. Okay, clear? That is what I told by meaning of complete reversal. Now coming back to the feed forward process. In feed forward process, what happens is there is no variable that is going to act on your sense organ. This is going to act by anticipation. Very easy example, I'll tell you. You all will be like thinking to have food, right? When you're going to thinking a thought of having a food, what happens? You're going to have a salivation. So there is a salivation on thought of food. Okay, on thought of food. So this is one example for your feed forward mechanism. Number two, when there is going to be raise of heart rate in any emotional situation, or when there is going to be raise in metabolism of your body, when you're going to start your exercise, even while starting your exercise, okay, your body will be preparing for the metabolism. And very fine example is behavioral thermoregulation. Always remember, thermoreceptors is the hypothalamus, so absolutely no physiological process are involved. Then your example, another example is role of your cerebellum in the motor coordination. So you are going to walk, your cerebellum is going to be taking a precaution. It is going to be trying to make sure that you are not falling down. That is one example. Thinking of exercise itself will be increasing your heart rate. That is your anticipatory tachycardia. And then gastric acid production while thinking of food. All these things are going to be feed forward process. Is it clear? So with this, we are completing the first part, that is going to be your homeostasis. Next, we are going to move towards the intracellular communication. So what is the intracellular communication? Always remember, this is very, very important. So until now, I don't know how many of you are listening, but from here you should be having attention, because intracellular communications are very, very important for any systemic. You take whatever you're going to read in your systemic physiology, this is what which is going to have an important application. Clear? So now let me start with, so what happens? So there is a transportation, there is a communication between two cells. This can be either contact dependent, or it can be depending on a soluble factor. So what is contact dependent? So there should be an attachment between the two cells. Either it can be by a gap junction, either it can be by a cell to cell adhesion, or there can be any direct mechanical stress or any membrane bound signals. Soluble factor means there is no direct connection between the two cells, but ultimately what happens, there is going to be transportation. There is going to be a transportation of signals between two cells. So this is what called as soluble factor intracellular communication. I am very sorry, it is not intracellular, it is intercellular. Okay, it is between the two cells, it is intercellular communication. So what is autocrine? Autocrine means, so there is a hormone production inside the cell. That hormone is going to be acting, hormone or any signal mechanism that is going to act on the cell which produced it. That is called as autocrine. Paracrine, when the cell is going to produce some signal that is going to act to the adjacent cells, that is going to act to the adjacent cells, you call it as paracrine. What is a endocrine? So somewhere it is produced that is going to be going through your bloodstream to act on some other organ, that is called as endocrine. Example is your hypophyseal axis, all your thyroid hormone, everything. Okay, or it can be a synaptic, post-synaptic nerve transmission. So these are the various cellular transmissions. Is it clear? So in this cellular transmission, remember, it is going to be facilitated by, all these transmissions are going to be facilitated by certain transporters. So it is going to be transporters, certain transporters are going to facilitate. So what are those transporters? Imagine these are the two cells. Okay, so these are the two cells which are going to be present. So this is going to be your apical site and this is going to be your basal site. And here you're going to have a blood vessel. Here you're going to have a blood vessel. Here you're going to have a big blood vessels. Okay, here you're going to have the bed, or you call it as a extracellular matrix. So this is going to be extracellular matrix. Now you're going to have one cell. This is going to be the second cell. Between the two cells, what happens? There is going to be a tight junction. So here what happens? You will be having a tight junction. What is the role of this tight junction? This is going to be inhibiting your paracellular transport. This is going to inhibit your paracellular transport. And second thing which is going to be present, that is called as adherence junction. That is called as adherence junction. So what is adherence junction? Again, it is going to be a simple mechanical obstruction of signaling between two cells. Clear? Now, third one is going to be your desmosomes. So what is a desmosomes? Desmosomes are, again, it is going to be like this. So these are going to be the desmosomes. These are again going to prevent the transmission. And fourth one is going to be your gap junction. So what does your gap junction does? Yes, here the transmission occurs, but this transmission, this communicating junction is going to be managed by a system called as connexons. So this connexons, again, it will be having 6 units, that is called as connexins. We will discuss about it. And you have some non-classical junctions, and finally you have hemidesmosomes, that is not going to be connecting, rather it is going to be presenting with the extracellular matrix. So these are going to be your hemidesmosomes. Now you have 3 important things I told you: tight junction, adherence junction, and desmosomes. So I have told about 3 important things. What are the 3 important things? Tight junction, adherence junction, desmosomes. Number 1, let me start with the tight junction. Number 1, let me start with the tight junction. So what is going to be your tight junction? So what happens in your tight junction? I'll tell you. In tight junction, what happens is, okay, this tight junction is otherwise called as zonular occludence. It is otherwise called as zonular occludence. You just copy this entire tabular column. It's very useful for you. So tight junction is otherwise called as zonular occludence. Okay, this is going to be having 3 types of proteins. Number 1, claudin. Number 1, claudin. Number 2, occludin. Number 2, occludin. And number 3 is going to be your junctional adhesion, junctional adhesional molecule. Junctional adhesional molecules. Okay, these are the 3 proteins that is going to be present. What is the significance? Always remember, it is going to act as a barrier. It is going to inhibit paracellular transportation. Paracellular transportation. It is going to be inhibiting paracellular transportation. So where it is going to be playing an important role in the pathophysiology? Number 1, this when this tight junctions are going to be affected. Example in your Vibrio cholera. Okay, in the enteropathogenic Vibrio cholerae, what happens? This tight junction is going to be destroyed. Because of this, what happens? There is going to be a diarrhea. So for a any blood-borne metastasis, it is going to be occurring because of the pathology in your tight junction. Okay, next is going to be your adherence junction. What is adherence junction? It is otherwise called as zonular adherence. So it's otherwise called as zonular adherence. Okay, what is the proteins that is going to be playing an important role in zonular adherence? It is going to be E-cadherin gene. It is going to be E-cadherin protein. This E-cadherin protein is a calcium dependent. What is the role of your E-cadherin? They are going to be helping in the cellular integrity. As the name suggests, E-cadherin is going to be important role in the cellular integrity. Okay, and other thing is going to be, it is going to be helpful in tissue morphogenesis. It is going to be helpful for tissue morphogenesis. Okay, so what is the pathophysiology behind it? It is going to be helpful in cardiomyopathy. It is going to be helpful in cardiomyopathy. It is going to be present in the arrhythmias. So what happens? I'll explain you. This E-cadherin is the one that is present in the between your cardiac muscle, between your cardiac myocytes. Whenever this example, for example, you just imagine you will be having 25 members to 30 members who are sitting in a row in your class. So first bench la 25 people are going to be sit. For example, these 25 are present in a line. Okay, if one person is going to be pushed, he is going to stimulate all the people in that row and everyone will be pushed towards one side. For example, what happens if I am going to remove one person in the middle? What happens? This communication is going to be present only to the 5 or 6 students. When I remove the 7th student, from the 8th till 25, there is no communication. Because of this, what happens? These 5 are going to move in a separate direction. Those 7 are going to move in the separate direction. So therefore, what happens? There is going to be independent movement. That is what you call it as a arrhythmia. What is arrhythmia? When there is no coordination between your two ventricle or between the atria and ventricle, between the two cardiac myocytes. What happens? There is going to be a non-synchronous muscle contraction, because of which there will be arrhythmias. So that is occurring. Why? Because there is a damage to the adherence junction. Now third one is going to be your desmosomes. Desmosomes are present in the macula. It's otherwise called as macula adherens. It is otherwise called as macula adherens. So what are the proteins that is going to form? Number one, desmosomal cathecin. Okay, number two, it's going to be desmoglians. So I think you would have read about these two, desmosomal cathecins and then desmoglians. So what is the role of them? They are going to be important in epithelial. They are going to be playing important role in epithelial integrity. They are going to be playing important role in epithelial integrity. So what is the pathophysiology? What is the importance behind this desmosomes? So have you heard about Pemphigus vulgaris? Have you heard about Pemphigus vulgaris? Someone? It's a common dermatological condition. What happens in Pemphigus vulgaris? So Pemphigus vulgaris is caused by either lupus or penicillin or cephalosporin. So these are the two drugs and one condition which causes Pemphigus vulgaris. Okay, so what happens in this is you will have a pain or unbearable pain will be there. There will be a involvement of mucous membrane. There will be involvement of mucous membrane. And third one is there is a positive Nikolsky sign. I don't want to confuse you with what is Nikolsky sign. Just I'll give you a short note. So what happens? Pemphigus vulgaris nothing but some swelling. Okay, just remember like some swelling in your skin. So there is going to be a lesion in your skin. So when you're going to just scratch it, when you're going to slide it with a glass slide, when you're going to slide that Pemphigus with a glass slide, what happens? It is going to cause blanching. That is called as Nikolsky sign. This is negative in another condition. Why I am talking about Pemphigus vulgaris? There is another condition called as bullous phemicoid. There's other condition called as bullous phemigoid, where you will be having exactly opposite. You won't have pain in bullous phemigoid, only you will be having a pruritic itching, and there will be no mucous membrane involvement. There is going to be negative Nikolsky sign. So who is going to cause this? Bullous phemigoid. That is what the next one which we are going to see, hemidesmosome. You have seen desmosome. What is hemidesmosome? That is going to connect with the basement membrane. Who is going to be connecting the cell with the basement membrane? Integrin. So this is going to it's going to be connecting with the basal lamina. So when there is going to be damage to this integrin, it is going to cause bullous phemigoid. Is it clear till now? Till now, do you have any doubt? With this, we are completing the very important simple mechanical transporter, simple mechanical intracellular communicator. Next, we are going to move towards the last important point in the intracellular communication, that is your gap junctions. I think I have covered hemidesmosomes. Now I am going to talk about the gap junction. So if you have any doubt till this, you can just put in the chat box. Just give me a few seconds for having water. So within this time, you can just put any doubts if you have in the chat box, so that we can continue with the gap junctions. Okay, if you are not having any doubt, let me move towards the gap junction. What is the gap junction? Always remember, so till now, whatever I was talking, all these things are going to be not communicating. They are not going to be communicating, but okay, they are going to be just present for the integrity of the cell. This tight junction, adherence junction, desmosomes. But this gap junctions, it is communicating junction. It is going to be a communicating junction. So it is going to be a 2-cylinder. Okay, it is going to be 2-cylinder, but remember, these 2 cylinders are not going to touch each other. One cylinder is going to be inserted to the one cell, and others is going to be inserted into the other cell. Can you see here? This into this gap junction, this molecule, this cylinder is going to be inserted into this cell, and this cylinder is going to be inserted into the second cell. So it is going to maintain a communication between the intracell of 2 cells. Internals between the 2 cells, this is going to communicate. Who is going to communicate? 2 cylinders, but they are not going to touch each other. What is this cylinder called as? This cylinder is called as connexons. This cylinder is called as connexons. And what is this connexons are going to have? It is going to have 6 units. This connexons are going to have 6 units. So these 6 units are called as connexins. So this 6 units, they are going to be called as connexins. So this connexins, 6 connexins together, they are going to form connexons. So why it is important? This cell is important in 3 important places. Number 1, in a cardiac myocyte. In a cardiac myocyte, you require this gap junction for communication. Number 2, smooth muscle cells. Smooth muscle cells. Okay, whenever there is going to be a problem in your gap junction, whenever there is a problem in your gap junction, you are going to have number 1, Kitts syndrome. What does Kitts syndrome stand for? I'll tell you as a mnemonic. K stands for keratitis. Then keratitis, inflammation of your epithelium. Okay. And what is I stands for? Ichthyosis. I stands for ichthyosis, and D stands for deafness. D stands for deafness. So these are the 3 important syndrome. And number 2 is your Charcot-Marie-Tooth syndrome. This is not a tooth. It is not a tooth syndrome basically. You can just go and search. This is going to be a Charcot-Marie-Tooth syndrome is the one that is going to cause some arrhythmias, because there is no smooth transmission of impulses in your cardiac myocyte. As I already told you, for example, as adherence junction, same thing here it is going to occur. This is the gap junction. Clear? Now, with this, we are completing the intracellular transportation. Next, we are going to intracellular communication. Next, we are going to move towards the transportation across the membrane. So, you have 2 important transportation, exocytosis, endocytosis. What is exocytosis? When there is a extrusion of protein out of the cell. That is called as exocytosis. Endocytosis means when you're going to make the protein entry into the cell, when you're going to bring the protein inside your cell, that is called as endocytosis. I think it is clear for you. Now, moving on towards the transport mechanism. Broadly, all your transport mechanism are divided into active and passive processes. Active and passive processes. This passive process, I can call this as passive mechanism. This passive mechanism is again divided into simple diffusion or facilitated diffusion. Third thing is going to be osmosis. Number 1, simple diffusion. Number 2, facilitated diffusion. Number 3, osmosis. What is a diffusion? Now tell me, what is a diffusion? So a diffusion is nothing but a movement of molecule from the area of higher concentration to the area of lower concentration. That is your diffusion. That is your passive transport. So what happens here? It is going to moving from higher concentration to lower concentration. What? Solutes. Okay, solutes are going to be moving from higher concentration to lower concentration. In an active transport, what happens? Your solutes are going to be moving from the lower concentration to higher concentration. And what happens in your osmosis? Here, instead of solute which is going to move, here the solvent is the one that is going to move. Here the solvent is the one that is going to move. Now you're clear, I guess, what is a osmosis. Okay, so now you all understood these three things. Now moving towards the first one, your cell membrane. Your cell membrane is playing an important role in the transportation of molecule. The bilayer of your cell membrane are going to serve as a barrier between your extracellular fluid and your intracellular fluid. So your lipid soluble substance is going to penetrate the lipid bilayer of the cell membrane by diffusion. So that is going to be your simple diffusion. So in a simple diffusion, what happens? All the lipid soluble substance are going to penetrate your phospholipids. It's going to penetrate your phospholipid and it's going to enter. That is your simple diffusion. Whereas the one that is not very easily penetratable in your lipid soluble substance, then it has to move toward a carrier. So who is going to be acting as a carrier? Your transmembrane proteins are the one that is going to act as a carrier. Okay, so that is going to be a carrier. So this is your simple diffusion. Okay, the carrier proteins are going to facilitate, which is going to facilitate your carrier diffusion. So this carrier protein, when it is going to facilitate, but there is a movement of transportation from the lower solute concentration to a higher concentration to a lower concentration, then you call it as a passive transport. When the same proteins are going to help with the presence of ATP usage, when it is going to be helping for the solute transportation from a lower concentration to a higher concentration, then you call it as an active transport. Is it clear till now? Now we are going to move towards what is a simple diffusion. It refers to the random molecular movement of substance through intermolecular space in the cell membrane. I already told you there are some phospholipids. For example, here you are going to have phospholipid. This is going to be a phospholipid. This is going to be a phospholipid. Then you are going to have a membrane. So this is going to be a phospholipid. Okay, then you're going to have a phospholipid, then you're going to have a phospholipid. So between the two phospholipid, when it is going to enter, that is called as your simple diffusion. So that is called as a simple diffusion. Okay, so the diffusion means movement of molecule from the higher area to a lower area. Who is going to govern the entire diffusion? It is governed by Fick's law. I'll tell you FICKS, Fick's law. I'll tell you at the end of the discussion of this diffusion what is Fick's law. Okay, now what is a simple diffusion? For example, your diffusion of lung. Okay, your diffusion of your lung is going to be a simple diffusion. Okay, your diffusion is going to be along the concentration gradient. Underline this. It is going to be along the concentration gradient. So simple diffusion is going to either occur through the lipid bilayer or it is going to be occurring through the protein channels. So your lipid solubility of substance is determined by ability to diffuse through the cell membrane. For example, your water can be moving through your, your water is going to be insoluble to your lipid that diffuses through protein channel. Okay, that is going to diffuse through protein channel. For example, gases. So these gases are lipid soluble substance. Therefore, they are going to penetrate your lipid lipid bilayer and they are going to enter. So these are the two examples which I can give you. So remember always what are the properties of the solutes which are going to enter. So your solutes should be extremely small. Your solutes must be extremely small. It is going to be non-charged. It shouldn't be charged molecule. Okay, it shouldn't be charged molecule. Why? Whenever there is going to be a charge, there is going to be a sphere of hydration. Whenever there is a sphere of hydration, it is going to become lipid insoluble and it cannot enter your lipid bilayer and it cannot go by a simple diffusion. In that case, okay, if it is going to be, then what happens? It cannot go through the simple diffusion. Then it has to go through some aquaporins. It has to be going through aquaporins. That is what you call it as a facilitated diffusion. That is what you call it as facilitated diffusion. For example, it must be carrier mediated diffusion. Simple diffusion process is going to be facilitated by a carrier protein. For example, GLUT, glucose transporter. So this is going to be helping the transportation of glucose. For this is called as a facilitated diffusion. Other example is your aquaporins. All your aquaporins are going to be facilitated diffusion. So there are 12 aquaporins present, and that aquaporin 6, aquaporin 7, all are present in your kidney. Okay, aquaporin 11 is present in your kidney. Okay, all these things are very important. So what happens here is the diffusion of substance is going to occur through cell membrane with the help of a carrier protein. Here it is going to be help of a carrier protein. Why you need a carrier protein? Because here there is going to be a movement of a charged molecule. All your charged molecule will be having hydration. Therefore, it cannot enter through phospholipids. Therefore, it has to be transported through a carrier protein. It is going to be transported through a channel. Okay. But again, this transportation is also going to be following from a higher concentration to a lower concentration. So it is also going to follow higher concentration to the lower concentration. Clear? Now you're going this. Can you see? You have some, for example, so a classroom has 4 doors. Okay, in that 4 doors, you're going to close all the 3 doors and only 1 door is open. Okay, all are ready to get outside the class, but only 1 door is present. Only 2 at a time can go. Okay, you need a door to get out. You cannot go as such. You need a door to get out, but you have only 1 door at a time. You can go, only 2% can go, but there are 10-20 people inside. What happens? You can till 2% goes, there will be increase in the graph. That is increase in the rate of a disappearance from the class. But what happens once 2 people goes, then slowly only you can get, you can just enter, get out of the class. So that is called as that is what you are going to talk in the Michaelis-Menten kinetics. What is Michaelis-Menten kinetics? Michaelis-Menten kinetics is telling that you have only defined channels. Only through these channels your molecules has to go from the extracellular space to intracellular space or vice versa. But what happens? You have limited number of channel proteins. So this, the point where it reaches the maximum point, that is called as your Vmax. Okay, so there is going to be increase in the rate of diffusion. That is the speed of transportation. But at one particular point, the velocity is going to become gradual. So example, a door can be like occupying 7 to 8% at a time they can go out. So till 8% goes, your graph will be increasing. That is the speed of transportation will be increasing. After that, only 8 people can get out. For example, you have 4 more doors, isn't it? I'm opening all the door. Now, in 4 doors, 8 people can get out. So, only 8 people can get out at a particular time, not more than that. That means your Vmax is going to become 8 people. But not more than 8 people can get out that particular second outside the class. So, that is what your velocity max is defined. But in simple diffusion, you don't have any door. It is a plain open ground where the people can get out. So therefore the rate of diffusion is going to be slightly increased increasing, that is linear extrapolated increase. So as long as your concentration gradient is present, there is going to be a rise in the rate of diffusion. That is going to occur in the simple diffusion. Whereas in your facilitated diffusion, it is going to be depending upon, okay, in facilitated diffusion, it is going to depend upon two important concepts. It is going to be determining, it is going to be the one which is going to determine the rate. There are two things. One is your concentration gradient. One that determines is your concentration gradient. Second is the channel property. That is how big your door is. So whether the door can accommodate one person at a time or whether the door can attend two person at a time. And similarly, how many doors are there? That is how many channels are there? That is the number of channels. So one is the concentration gradient. Second is your channel properties. What is the caliber? What is the caliber of the channel? And then what are the number of channels that are present? So this is what Michaelis-Menten kinetics defines in the facilitated diffusion. Okay, what that is going to define in the facilitated diffusion. Is it clear? I think is it clear? Okay, now remember, so the transported molecule is facilitated diffusion is going to bind to the one side of the carrier protein, following which other side is going to open. Then the weak binding molecule causes it to detach from the protein and deposit to the other side. So for example, this is going to be your channel protein. First, what happens? There is going to be attachment at this point of time. So at this place, it is going to attach. This is going to move down and it is going to slowly get out. Similarly, at the same time, here you are going to have another one who is going to go out like this. Okay, va? So this is called as your facilitated diffusion. When it is reaching the maximum limiting point, okay, the rate at which the molecule is transported via mechanism can never be greater than the rate at which your carrier protein can undergo. So carrier protein evlo irukko, how many carrier proteins are there? And at the same equal point only your transportation also can occur. So that is what your Vmax is. Is it clear? Can you understand what is a Vmax? So it is two things which are going to affect the net rate of diffusion is number one, concentration gradient, and number two is going to be the effect of membrane potential. That is your Nernst potential. Okay, now very important thing, next one what you are going to see is the two important formulas or two important equations. The one is going to be a fixed equation. So your simple diffusion is going to be governed by the simple diffusion is going to be governed by this rate of diffusion. That is your Fick's law. What does your Fick's law says? Rate of diffusion is directly proportional to the concentration gradient into, okay, concentration gradient into surface area of the membrane divided by thickness of the membrane into diffusion coefficient. So now tell me, what is the one that is going to be the determining factor for the simple diffusion? Number one, concentration gradient. Number two, thickness of your cell membrane. When there is going to be increase in the concentration gradient, there is going to be increase in the rate of diffusion. Whenever there is going to be increase in the surface area, there is going to be increase in the rate of diffusion. Whenever there is going to be increase in the thickness, that is going to cause decrease in the rate of diffusion. And what is this diffusion coefficient? Again, this diffusion coefficient is estimated by Stokes Einstein equation. You don't need to mug up the equations which is present in the guide 10. Okay, in the guide 10, you don't need to mug up all the equation. Just remember the name, Stokes Einstein equation. That is the one which is going to govern the diffusion coefficient. Okay, so what is the diffusion coefficient? Diffusion coefficient is directly proportional to your temperature, inversely proportional to the viscosity, and it's going to be the radius of your solute. Now tell me, what are the one that is going to be determining the rate of diffusion? Number one, together with me, concentration of the gradient. Number two, increase in the surface area of membrane is going to increase the rate of diffusion. Number three, decrease in the thickness of membrane is going to cause increase in the rate of diffusion. Number four, increase in the temperature causes increase in the rate of diffusion. Number five, viscosity means stickiness. When there is a stickiness, that is going to cause reduction in the rate of diffusion. Similarly, when there is going to be increase in the radius of solute, then there is a decrease in the rate of diffusion. Clear? This is what your Fick's law says. This is what your Fick's law says. Is it clear? Now coming back to the question asked by Uday in the chat box. Sir, can we discuss the intracellular communications again? I'll tell you there are 4 intracellular communications shortly. Tight junction, adhering junction, desmosomes and hemidesmosome. Tight junction, it is called as zone of occludence. Okay, it is called as zone of occludence. So it is going to have 3 protein that is going to be preventing the paracellular transport. Adherence junction, it is a E-cadherin that is going to be helpful in cellular integrity. And desmosomes, they are going to be present in the epithelium. They are going to be helpful in epithelial integrity. And hemidesmosomes are the one which is going to be attaching with the basal membrane. That is going to be helping you for cellular integrity again. Along with it, it is going to be helpful in integration with the basement membrane. And you have the gap junction. So they are the communicating junction. They are going to be essential for molecular transport between one cell to other cell. For example, cardiac myocytes. These are the 5 intracellular mechanism. Okay, I think it is clear now. Let me move towards a very important topic that is going to be this is your Michaelis-Menten equation. Michaelis-Menten equation. This is very important. So this equation. If you want, you can remember. Otherwise, just remember there are 3 factors which I told you already. What are the factors that is going to be playing a role in the Michaelis-Menten kinetics? Concentration gradient, channel protein and channel property, and number of channels which are present. So these are the 3 important things that is going to be playing a major role. Clear? Now let me move towards the third important thing, that is the active transport. Here also you are going to have a transport protein, membrane protein, but what happens this is going to be helping in transportation by movement of solute from a lower concentration to higher concentration. Usually flow is from high to low, but here there is going to be flow from low to high. Therefore, you need some energy. How you are going to derive this energy? Okay, so for example, just consider this is going to be your ECF, this is going to be your ICF. Okay, your ECF will be predominant in sodium, your ICF will be predominant in potassium. Am I right? Okay, now you want to transport sodium from the intracellular to extracellular. Already sodium amount is going to be low in the intracellular area. Now what you want to do? You want to bring the sodium from the ICF to your ECF. This transportation is going to be followed by. But what happens is, when you're going to take some sodium outside the ECF, from your ICF you want to take to ECF, then what happens? You need to balance. So there is going to be loss of positive ions from your intracellular space. You need to balance that. For that, what you do is you bring potassium back to your ICF. Already potassium is more in the ICF. Now you are going to bring from the area where potassium is less in the ECF to the ICF where potassium is more. That means here the flow is going to be from a lower concentration to a higher concentration. Yes. So it is going to be from the lower concentration to higher concentration. For this, what you need? You need a molecule called as ATP, which is the energy for your cell. How you can bring ATP? Okay. There is an enzyme called as ATPase. So enzyme called as ATPase, which is going to break down your ATP to give energy. So wherever you're going to have ATPase enzyme, that you call it as primary active transport. Primary active transport. So wherever you're going to have ATPase enzyme, it can be 3 sodium 2 potassium ATPase, sodium potassium calcium ATPase. There are lots of ATPase. So whenever a ATPase enzyme comes and plays a role, then you call it as a primary active transport. Now moving towards the second one, that is going to be a secondary active transport. Before moving towards the secondary active transport, in primary active transport, remember all the molecules are going to be moved against their concentration gradient. So here what happens? There is going to be ATP hydrolysis. Here there is going to be ATP hydrolysis. So one fine example is your sodium potassium ATPase pump. Okay, I wanted to talk about the sodium potassium ATPase pump because this sodium potassium ATPase pump, I can tell you, it is going to be like these 3 important structures are going to be there. Okay, three important structures are going to be there. This is how your sodium potassium ATPase will be there. You will be having an alpha unit, you will be having a beta unit, you have a gamma unit. Two alpha unit, two beta unit, two gamma unit are going to be there. Okay, this is going to be the number of subunits. You have three subunits, alpha, beta, gamma. Okay, what are the one that is going to be sitting on the only alpha units among these three are going to be playing a role in the sodium potassium transport. Okay, so from where you need to transport sodium to where? So you need to transport sodium from the intracellular fluid to your extracellular fluid. So where is going to be your sodium sitting? In the ICF side. This is your ICF, this is your ECF. On the ICF side of your alpha subunit, your sodium is going to be sitting. Along with sodium, you will have ATP, you will have ATPase. And in the extracellular side, you will be having potassium. Along with potassium, two other things are there. One is digoxin, one is dopamine. Okay, one is digoxin and other is going to be uabine. Okay, digoxin, other is going to be a uabine. Okay, so alpha is the one that is going to be involved in the transportation, not beta or your gamma. Now, your beta units, what it is going to do? Your beta units are going to be helpful for glycoxylation. So, it is going to be attaching with glucose. Your beta unit is going to attach with the glucose. Now, tell me, what is the role of a sodium-potassium pump? Sodium-potassium pump is helpful for maintaining the resting membrane potential. Maintaining the resting membrane potential. Second one, they are going to maintain the cell volume. They are going to maintain the cell volume. So these are the two important functions of your beta sodium potassium ATPase. How it is going to be? Okay, I'll tell you. Sodium potassium ATPase maintains the difference in the ionic concentration between your ICF and ECF, number one. Number two, it maintains the resting membrane potential. Number three, they are going to maintain the cell volume. Number four, they are going to be helpful in secondary active transport. Okay, it is also going to help in secondary active transport, but main role comes in the primary. And number five, accounts for large part of the basal metabolic rate. Now tell me how this activity is going to increase. So the activity is of ATPase are going to be increased by your number one, thyroid hormone. So when there is more synthesis of thyroid hormone, there will be more activity of your sodium potassium ATPase. Second one is your insulin. Okay, your insulin is going to increase the activity. So example, in a hyperkalemia, let me take in a hyperkalemia. Okay, it is going to helpful in reuptake, okay, of potassium into the cell by increased activity of your insulin of sodium potassium ATPase. Okay, now what happens when there is going to be decrease in the activity? Number one, your dopamine. Number two is going to be your number one dopamine. Number two is your digoxin. Okay, so what does this do? So digoxin is going to be usually causing toxicity. But you know that your digoxin is going to sit in the ECF side of your alpha subunit. Okay, so potassium illa. Okay, just imagine two conditions. So I'm going to tell two conditions. Okay, one is when there is excessive potassium. When there is excessive potassium in hyperkalemia. Okay, and second thing is going to be decreased potassium. Okay, there is going to be excessive potassium, there is going to be decreased potassium. But what happens? You have only one alpha subunit, and this one site can be bound either by potassium or by digoxin. Okay, so when there is hypokalemia, what happens? No potassium is going to be available. No potassium is going to be available. Therefore, more digoxin can bind. More digoxin can bind. Okay, in a normal digoxin therapeutic dose itself, in a hypokalemic patient, so this is going to cause more digoxin attachment and it can lead to digoxin toxicity. How can you find your digoxin toxicity in a ECG? In a ECG, the digoxin toxicity is represented by depressed T wave. Depressed T wave. Okay, so you will have a depressed T wave. Just remember, mug up for now. When you remember, when you're going to read about ECG in CVS, you can understand it. So there is a depressed T wave digoxin toxicity. Now coming back to the increased potassium. So in a hyperkalemic patient, In a hyperkalemic patient, what happens is your digoxin is there. Your digoxin, okay, is going to in turn cause hyperkalemia. How I will tell you, there is a digoxin toxicity. When there is a digoxin toxicity per se, what happens? It is going to stimulate more transportation of your sodium outside. Whenever there is more transportation of sodium outside, equal amount of potassium has to enter inside. So more potassium enters to the intracellular fluid. Therefore, it is going to cause hyperkalemia. It can cause hyperkalemia. So hyperkalemia, how it is represented? Tall T wave, tall tented T wave, tall tented T wave. This is not very important for you as of now. Just remember the name alone. Okay, now you can understand, right? Now, second thing is going to be, you're going to move towards the secondary active transport. Till this, if you have any doubt, you can put in the chat box so that I can move towards the next point, that is a secondary active transport. Shall I move into the next aspect? Secondary active transport. Yes. So what is a secondary active transport? Here also your sodium is going to move along your concentration gradient. Here also it is going to be moving along the concentration gradient. But the second molecule is going to move against the gradient. That is, for example, let me tell you, you're going to have a ECF, you're going to have a ICF. Okay. So this is going to be a transportation protein. Okay, here your sodium is going to move from extracellular to intracellular. That is from higher concentration to lower concentration, isn't it? From higher concentration to lower concentration, your sodium is moving, I accept. But in a calcium, what happens? Here ECF, it's going to be higher concentration, and in sodium, it's going to be, in ICF, it's going to be lower concentration. Even in spite of that, your calcium is going to move outside. Your calcium is going to move to outside. This is going to be opposite. So this is going to be with gradient, and this is going to be against your gradient. So what sodium calcium, okay, transporter? This sodium calcium transporter is going to be there, right? This is going to be always dependent on the extracellular sodium level. Since sodium is more in the extracellular, so sodium level base பண்ணி தான் உங்க calcium level இருக்கும். So இது வந்து என்ன பண்ணுது? One moving from ECF to ICF. Other is moving from ICF to ECF. So this is going to be in opposite direction, right? Whenever it is going to move in the opposite direction, you call it as antiporter. You're going to call it as antiporter. For example, you're going to have a thing. Okay, this is going to be your ECF and this is going to be ICF. Your glucose is going to enter from ECF to ICF, but along with glucose, your water is also going to enter from ECF to ICF. This transportation is going to be in the same direction. You call it as symporter. You call it as symporter, or you can call it as co-transport. Antiporter is otherwise called as counter-transport. Okay, so what is the example of a co-transporter? Co-transporter example is going to be your SGLT. Okay, your S-glut. Okay, so what does your S-glut do? That is going to be helpful for transportation of your glucose. Okay, that is going to be S-glut. Okay, so sodium and glucose is going to be transported across your intestinal epithelial cells and renal epithelial cells. So that is going to be your S-glut. That is a co-transporter. Okay, what is a counter transport? Sodium calcium is going to be a counter transport. Sodium hydrogen, that is going to be a counter transport. Okay, so that is going to be called as counter transport mechanism, that is going to be regulating your acid base metabolism. Okay, with this we are completing a very, very important transport mechanism. Now we are moving towards the third important transport mechanism, that is your osmosis. What is osmosis? Till now in the transportation, both active, secondary active, primary active, and in your diffusions, whatever we discussed is where the solute is going to move from the higher concentration to lower concentration, or lower concentration to higher concentration. But here, in a simple terms, here your solvent is going to move. That is, your water is going to move. You know that most abundant substance that diffuses through the cell membrane is your water. Okay, so the amount of water that diffuses both sides of your cell membrane is equal to 100 times of the volume of cell. However, the amount of water that diffuses on either side has to be balanced so that your volume of cells should not get more or less. Okay, so it should not go hypotonic or it should not go hypertonic. So that is a very important thing. Who is going to maintain? That is the osmotic gradient. So the net movement of water due to the concentration difference is termed as osmosis. Okay, wow. So osmosis is the example I told you. Okay, now what is the osmotic pressure? The amount of pressure required to stop osmosis is called as your osmotic pressure. So the mole is a, okay. Now what happens? You are the osmotic pressure is the pressure that is required to stop your osmosis. In a situation where there is a water on A side of the membrane and NaCl is on the B side, what happens? So there should be some amount of pressure applied to the B side to stop the water transportation from the into the same side of water. So in the side la varama tadukkanum. Adukku in the side la or pressure irukku. Adudha osmotic pressure. That is what called as osmotic pressure. Okay, so it is determined by the number of molecule in the solution and not by the mass of the molecule. So now you are going to define the term osmolarity. So you have two terms. Osmolality, osmolarity. What is osmolarity? Number of osmoles per liter, you call it as osmolarity. Okay, osmolarity. Number of osmoles per kilogram of solvent, you call it as osmolality. But usually osmolality osmolarity molarity is the one which we will be seeing. Okay, now you know difference between osmolality and molarity. Now what is the difference between osmolarity and your osmotic pressure? Osmolality means at a normal body temperature of 37 degree, the concentration of 1 osmol per liter will cause 19,300 millimeter of mercury of osmotic pressure in the solution. Or I can tell you 1 milliosmol per liter is equal to 19.3 millimeter of mercury of osmotic pressure. So this is what osmotic pressure constant which we will be dealing. But I will tell you this is not required for you. Okay, now what is important for you is remember osmolality. So osmolality is equal to, what is osmolality? Osmolality is equal to number of osmoles divided by kg of solvent. This is what it is important. Okay, osmoles are otherwise called as solutes. That is going to cause osmotic effect. So normal osmolality in a human is 270 to 290 milliosmol per kg. So this is normal. Okay, this is normal. Okay, osmotic gradient solvent will be moving from lower osmolality to the higher osmolality till there is a equalization. That is what your osmolality is. For example, your glucose urea is going to have 20, whereas it is going to be 2 in case of a plasma protein. Now, what is hypertonic? What is hypotonic? What is isotonic? These three you have to know. These three you are going to know. So at a steady state, ECF osmolarity and ICF osmolarity are equal. So just remember, this is going to be your ECF and this is going to be your ICF, isn't it? So this is your ECF and this is your ICF. Okay, so the osmolarity between the ECF and ICF has to remain equal. Even though the area is low for ECF and more 40% is ICF and only 20% is your ECF, even then, what happens is, even in that case, the osmolarity between the ICF and ECF should remain equal. If not, what happens? Your water will be moving from the lower concentration to a higher concentration. It is going to move from low to higher. I have told wrong. High to low. It will be moving from higher concentration to the lower concentration. To avoid that, even though there is a difference in the percentage of ECF and ICF, what happens is the body fluids are going to be same in the osmolality. That is what tonicity means. Okay, so the osmotic gradient is such that there is no transportation of fluid from your ICF to ECF in a normal condition. Okay, so for that, what is the osmolality that has to be maintained? 270 to 290. That is 270 to 290. So water will be flowing inside the cell and simultaneously water will be flowing outside the cell. So this is called as isotonic. When there is going to be less than 270, when it is going to be less than 270, then what happens? Water will be flowing inside the cell. That is called as hypotonic. Okay, when it is going to be more than 290, what happens? There is going to be flow of water from outside, from the cell outside. That is called as hypertonic. That is called as hypertonic. Okay, so now whatever IV fluids that you are going to give is going to be based on this concept. It is going to be based on this concept. For example, what are the example for isotonic fluids? Isotonic fluid example is your ringer lactate, 0.9% NaCl. So these are the two example of isotonic. What are the example of hypotonic? 0.45% of NaCl. Usually you can see in the casualty medical officer tells put off NaCl. Off NaCl means not off bottle of NaCl. It is 0.45%. Normal NaCl is 0.9% and you're going to put 0.45 in a hypotonic patient. Okay, hypotonic fluid. In a hypotonic fluid, you're going to give 0.45 NaCl. Hypertonic 3% NaCl you will be giving. 3% NaCl or mannitol. Is it clear? Can you understand this? Now I will discuss these 5 important things. So with this we can actually complete if needed. So what are these 5 important boxes? So these 5 important boxes are very important for understanding your ECF, ICF. Normally what happens? Your ECF volume increases, but there is no change that is going to occur in the osmolality. For example, I am going to put a normal IV fluid in the plasma. Even though I give a normal NaCl, 0.9% NaCl, that is not going to affect the osmolarity of your ECF. Therefore, there is no shift of water from the ICF to your ECF. Okay, for example, I'll tell you. So this is called as isotonic dehydration. Isotonic dehydration. So whenever there is going to be bleeding, whenever there is going to be diarrhea, whenever there is going to be burns, vomiting, ascites, there is going to be a reduction in the ECF volume. But at the same time, your osmolarity of your ECF or ICF is not going to change. Therefore, there is not going to be shift of your, there is no shift of your osmolarity. There is no shift of your osmolarity in a diarrhea case. This diarrhea case is called as isotonic dehydration, number 1. Number 2, what is when you're going to give an IV fluid, isotonic IV fluid, what happens? There is going to be increase in the ECF volume, of course, but there is no affecting the ICF, and at the same time, it is not going to increase the osmolarity. That is what you call it as. I can show you again. I'll draw and show you. So just consider this is going to be your osmolarity. Okay, this is going to be your ECF. This is going to be your ECF, and this is going to be your ICF. Okay, any doubt up to this? This is going to be ECF and this is going to be ICF. So this is going to be volume of your ICF. This is going to be volume of your ECF. Now, in isotonic dehydration, number 1, isotonic dehydration, what happens? The volume of your ECF is going to be decreased, but the osmolarity is going to remain constant. That is called as isotonic dehydration. Example is bleeding, sweating, diarrhea, burns, vomiting, etc. Okay, when there is going to be administration of isotonic 0.9% NaCl, there's an increase in the ECF. Yes, I accept. There's an increase in the ECF, but at the same time, there is no change in the osmolarity. This is called as isotonic administration of IV fluid. Isotonic administration of IV fluid. Third condition, I am going to administer hypertonic. I am going to administer hypertonic fluid. So what happens when I administer hypertonic? Okay, again, hypertonic means volume will be decreasing. So there will be decrease in the volume, but what happens? There is going to be increase in the osmolarity. So there is going to be increase in the osmolarity. Because of this, what happens? There is a shift of fluid. There is a shift of fluid. In order to compensate the hypertonicity, of your ECF, what happens? There's a shift of fluid from your ECF, ICF to your ECF. There's a shift of fluid. Therefore, what happens? Volume of your ICF also decreases. Overall, the tone of your ICF and ECF is going to increase. That is, so you will be having a curve like this. This is a normal, black is a normal one. But what happens? There's an increase in the osmolarity in both ICF and ECF, but there is a reduction in the volume. Is it clear? This is hypertonic dehydration. What happens in a hypotonic dehydration? In hypotonic dehydration, what happens is there's an increase in the volume of your ECF. Clear? So there's an increase in the volume of ECF, but what happens is, okay, so there will be a decrease in the volume of ECF. Ultimately, what happens? The osmolarity is also going to decrease. Okay, therefore, there's a shift of fluid from the ECF to your ICF. Instead of shift of fluid from your ICF to ECF, here what happens? There's a fluid shift from your ECF to your ICF. Therefore, ICF volume increases, ECF volume decreases, but there is a decrease in the osmolarity. This is called as hypotonic. This is called as hypotonic. Example, I'll tell each an example. For hypertonic, what are the example? Number one, diabetes insipidus. What happens in diabetes insipidus? So what happens? There is going to be a severe water is going to get lost in your urine because of aldosterone mechanism. So there's going to be loss of water in the urine. Because of loss of water, what happens? There is going to be increase in the sodium value in the body, but water value is less. Therefore, your body ECF will become hypertonic. Next, what happens in hypotonic? For example, in Addison's disease. In Addison's disease, in renal failure, what happens in all these conditions? There is going to be a increase in the water amount in the body in your ECF. So water increase and tone decrease. So in Addison's disease and all, sodium is going to lose excessively in your urine. When sodium is lost excessively in your urine, what happens? Your tone reduces and volume is also going to be considerably reduced. Why? Because there is going to be flow of water from your ECF to your ICF. There is going to be a flow of water from your ECF to your ICF. This is called as hypotonic dehydration. Now tell me, what are the how you can classify your glucose bottle? So glucose etrangla. So commonly you can ask in casualty. So take a glucose bottle. Is it glucose? No, it's a dextrose. Okay, so dextrose soda value usually 5% dextrose. It is isotonic. 5% dextrose is isotonic. When you're going to add 5% dextrose with NaCl, you're going to put it together, then it is going to cause hypertonic. So, veru 5% dextrose, only 5% dextrose is going to be isotonic. Whereas, when you're going to mix 5% dextrose and NaCl, 0.9% NaCl, this is going to become hypertonic. Okay, this is going to become hypertonic. So, what is the inference? So, when you're going to be in casualty, never mix the dextrose and saline NaCl and give. So, don't mix sodium chloride and your dextrose and give for the patient, because that is going to be considerably change the value of the tonicity of your body. That is going to considerably changing the tonicity of your body. Is it clear? So, I think this is going to be a more, I think we have completed already many important things. Okay, so next important thing is body fluid. I think body fluid we can discuss tomorrow. For today, I think this is enough. So for today, what all we discussed, we have discussed the entire passive transport mechanism, sodium, potassium, ATPase, osmosis. Okay, everything we discussed except your body fluid compartments. So body fluid compartments and your RMP, resting membrane potential. These two things alone we will be discussing tomorrow. So let's see tomorrow. Okay, any doubt you can ping me in the WhatsApp so that I will be clarifying it. So tomorrow let's complete this and let's proceed into hematology. This week we are going to complete the entire physiology. So that's all physiology is. Whatever you read in your Gaitan, whatever you read in Ganong, whatever you read in your Symbolingam, this is the concept. So once you understand this concept, you can write yourself for all the essay questions, short note questions, or your MCQs. So this is how I am just planning my session. So today I have completed the first part of your general physiology. Tomorrow I will deal with the second part of your general physiology and we will move towards the hematology tomorrow. Is it clear? Thank you so much. So have a good day.